It'd be a super good April Fool's joke. Can you hear me now, Josh? Can you hear me now? Can you hear me now?
Yes, I can.
I can't hear you because I don't have my volume on. Can you hear me? Okay, now my volume's on. Okay, you can hear. Cool. I'm glad that's all been recorded. Makes me happy. Hi, future people who are watching this. Hopefully you can hear as well, but apparently not the first little bit. Okay, so we have a flat surface. We're going to talk about the thermal boundary layer at one given snapshot, at one given point. Unless you guys all walk out, then I guess I'll just talk about it to myself. But as long as you're here, we'll do this. So we'll look at that, what that looks like. Let's give it some axes. So this is X and Y. And right, kind of the size of my arrows is the magnitude of the temperature. Okay, so longer arrows, higher temperature. The surface is hot, the fluid is cold. All right, we're done. Where are we? Okay, cool. It's a good day. 2 strikes. But we're still batting. Let's see if I can follow the next one off. All right, so up here, our temperature is really far away, T infinity. So we haven't felt the effects of the surface yet. We're still at the initial temperature. Down here, our temperature is T surface. At this point, we could describe convection at this point by our normal convection equation. So at this point, X QS double prime is the convection coefficient at X times TS minus T infinity, right? The normal equation. What we're trying to do is find what is H at this point. Okay, any ideas for how we could approach that? Do we know anything about the fluid flow? Somewhere that might be important. Yeah, Wally?
That it's not flowing at the surface.
Yeah, so we know that the fluid flow, as Wally said, we know that the fluid is not flowing at the surface. So how have we handled heat transfer in fluids that are not moving? Just conduction. So the only way at the surface itself, the fluid's not moving, so the heat transfer process must just be right in that surface layer. It must just be a conduction process. Right, because it's stopped or the no slip condition, QS double prime is minus K dt dy evaluated at y equals 0. So this is Just conduction through the fluid at the surface. Kf is the F is to say that this is for the fluid, not for the solid. So we can kind of generally describe what's happening by this equation, or we can describe it as conduction through the very surface of the fluid, but those two things have to be the same, because any fluid or any heat that goes through those first couple layers of fluid, eventually, because of conservation of energy, that heat is what eventually goes to T infinity. Right, the amount of heat that goes just in that first little bit eventually goes into the rest. So if we can figure out one, we can figure out the other. So this tells us that these two equations have to be equal to each other. So that must be true. And then we can rearrange to solve for H. Simply like that. So a couple things to note about this. Convection, the convection coefficient, like fundamentally what it's controlled by is conduction through that first little bit of fluid. So no matter kind of what else is happening farther away, what the really important part of conduction, because of conservation of energy, you have to travel through that first little bit of fluid before you can go out into the fluids, somewhere further away. That first little bit of fluid is stopped kind of by definition because of the no slip. So we have to travel through that fluid by conduction. So this gives us a couple things to kind of rules to think about for convection. So Kf, the thermal conductivity of the fluid, right? So this is obviously that's a fluid property. Ts, T infinity. Are constants. And H is proportional to temperature gradients at the wall. So convection is really conduction through that area right at the wall. This gives us a couple kind of rules of thumb to think about. So H is going to decrease as our thermal boundary layer grows. And what I mean by that, if we zoom out a little bit to our picture, right? This is the picture that we drew last time. When our thermal boundary layer is thin, we have a pretty steep slope right there. As our thermal boundary layer grows thicker, as we move from the left to right, that slope gets progressively less, and that slope is what's governing convection. So convection is going to be actually really good at the left side when we have a thin thermal boundary layer, and it's going to be relatively worse further along the plate when we have a thicker boundary layer, because we have less of a temperature gradient at the surface, right? The slope is less. So then kind of the corollary of that is anything that we can do to make the boundary layer thinner or to increase the slope there is going to be increasing convection. So the one way to do that, we saw this in the video, if you remember, we saw it with regard to the velocity boundary layer, but they're related. If we increase velocity, we don't give things as much, we don't give the boundary layer as much time to grow. So we should see, as we increase velocity, we should see the boundary layer get thinner. And we actually know exactly what that relationship is, right? We know that, right, kind of like we saw right here, it's a square root time. So a square root of the velocity. So if you doubled the velocity, you would increase convection by square root 2. So if you quadrupled the velocity, you increase convection by 2. So not only do we know just like kind of generally, but we actually know how these things are related. Okay. The second thing, which is similar but kind of interesting to note, is H decreases along the plate or along the X direction. For that same reason, the boundary layer is going to grow along the X direction, so the H value is going to be decreasing. Okay. We'll talk a little bit about kind of some more theoretical stuff about how we might find this in a second, but one of the things that makes this a little bit tricky is we've only ever been considering H as just like a constant value everywhere. But really, H is going to be something that's varying from one position to another position. So we kind of have to deal with that in a more sophisticated way, where H is going to be, if you're flowing over a flat plate, it's going to be really high at the front edge and it's going to be pretty low at the back edge of that plate. So we're going to have a fairly significant change in what that value is. So we'll look at find Q. Given a function for H. So this is going to be kind of an example of how we might do this. So we imagine, right, Q is going to be equal to the integral over the surface of Q double prime dA. So we're basically going to find the total amount of heat going from the surface by looking at every individual point and adding them all up. We can write this, because this is convection, we can still use kind of this old model. We just need something more sophisticated for figuring out what H is everywhere. DAS. So we still use this old model. We just have to have sophisticated ways of talking about what H is. So if TS is isothermal, so it's a constant, and T infinity, then break this is just simply TS minus T infinity, the integral over the area of H dA, or Q equals, we're going to change up our notation a little bit and call that H bar AS TS minus T infinity. So H bar is going to be the average convection coefficient. And we have to deal in averages because we have this kind of dynamic stuff happening at the surface where it is changing along the surface as boundary layers change. And this effectively is a way to make our lives back to as easy as it once was. So in effect, if we can figure out average convection coefficients, we can at least get kind of a ballpark picture of what's happening. But we're never going to get exactly the right picture because, again, in this case, we would have really good heat transfer at the front edge and relatively bad heat transfer at the back edge. And if we assume, you know, we're kind of painting with a broad brush and saying it's the same everywhere, it's just the average. That's not totally true, but a lot of times it can give us some idea into the performance, like into the heat loss. It can give us kind of, again, what we're trying to do in this conversation is develop intuition about what factors are important in H. How do we think about convection in different types of systems? And, you know, as we change different parameters, how does that change convection? All of those things. So a lot of times we'll, in this class, have, you know, some sort of exercise to determine average convection coefficient and then use that as normal. But actually figuring out what that is can be tricky in different situations. So our strategy find H bar, solve it per usual. This is still going to be obviously a simplification because it's compressing stuff that's very spatially, compressing it into an average. But it's going to be relatively good. So for a flat plate, H H only varies with X. It's like saying dH dz is equal to 0. So it only varies as we go like down the plate in the direction of the velocity, not as we go side to side. And it's flat, so there is no up and down direction. Because if we can move up, then we're all of a sudden off the plate. So it only varies down the plate in the direction of the velocity. So we can talk about an integral with just in the x direction. Okay, so our average convection coefficient is going to be 1 over the surface area times the integral over the surface area of H dA. Basically, we're going to add up H over the entire surface, and then if we divide it out by the surface, that gives us back the average. So this is just a straight way to calculate average. Our surface area equals length times width. So dA is width times a differential length. So this guy is in Z. That one is in the x direction, in the direction of the flow. So we can rewrite this as h bar equals 1 over L times the integral from 0 to L of h dx. And we'll use this. This is we'll use this to calculate average convection coefficients for flow over a flat plate. So here's our flat plate. Let's draw a picture. So there's the front surface. We have flowing onto our flat plate, a fluid flowing at some temperature T infinity. Our boundary layer is going to grow like that. So that's our thermal boundary layer, delta. This surface is at the surface temperature. Out here, we're still at T infinity. In the boundary layer, we're somewhere between T infinity and T surface. At any given point, let's say this point, let's imagine we know an equation for H. H at that given point. So let's say H equals H at X equals A X to the minus 0.1. And A equals well, A has maybe some weird units. So it has units that have to work out with our other units. So it has units of watts per meter to the 1.9 times Kelvin. Okay, so we have some function. There's a constant A that has these weird, goofy units, and this maybe gives you an idea, like we're going to be dealing with empirical relationships a lot of times because we can't necessarily always deal with exact relationships. But A is going to be, okay, related to the position, and it's going to change with X, or H is, rather. If we look at how H changes, so X, HX, it's going to be highest at the front edge, and it's going to be decreasing along the plate. HX of 0 is equal to A. And it's going to be kind of progressively decreasing as we go along our plate. If we want to find average convection coefficient, we do that by integrating using the equation that we just talked about. We integrate H, just AX to the negative 0.1 dx, which would be 1 over X times A 1 over 0.9 X to the 0.9 evaluated from 0 to X. Okay, so we end up with an X to the 0.9. So some of these integrals, when we're actually trying to find this, sometimes we'll end up with kind of weird equations. They'll feel a little bit weird. All we're doing is we have some function of X, we're going to be adding it up over the whole plate, and then finding the average by dividing by like the distance that we added it up over, which is X. So we added it up from 0 to X. That's like where this comes in. And then we got an average by this term where we divided out by X. Okay, so this would give us H bar is 1 over X. If we evaluate it from 0 to X, it would just look like that, which is equal to 1 over 0.9 A X to the minus 0.1. Or H bar 1.11 A X to the minus 0.1. So this looks a lot like our initial equation for H anywhere. So this is our equation for the average convection coefficient. But we can say the average is larger than the convection coefficient at any given spot. Okay, basically what we're doing is we're saying if we look here at this point and we want to calculate the average up to that point, it's always going to be bigger than the value at that given point because H is always decreasing. In this case, how much bigger? Well, it's 11% bigger. So H isn't always decreasing very slowly, but it's always going to be, the average is always going to be bigger than the value at a given point. Because Hx is decreasing. We can find average convection coefficients by integrating some function that we have. The last thing that we'll talk about is, okay, kind of related to this like video, at least still image that we showed because it didn't load right. This is just talking about a single flow regime. So what if we have something like this? We have a surface like this. We'll consider in this case, in this picture, the velocity. What's going to be happening for the first little bit is exactly what we talked about before. So we'll have, if we drew the velocity profile here, it would look something like this. But then after some distance, we could have this switch where we switch between laminar flow and turbulent flow. So what that looks like is all of a sudden our boundary layer kind of gets a little crazy. And we have, this is delta of x. But what we have in the boundary layer is this velocity, maybe not quite that much, but this gets significantly flatter. So there's much less of a much steeper slope at the surface. Again, if we kind of draw what's happening, so everything is nice and straight lines in the laminar region. There's going to be some region where, okay, these are still nice straight lines. And then we start to have stuff kind of starting to mix. And we all of a sudden have mixing and swirling, and things stop being well behaved. I'll draw things like that. So we're going to have two separate regimes. So this is all X. There's a regime where things are relatively behaving like one way. Laminar, which is really what we've talked about before. There's going to be some region which is a transition. And then another region where we have totally different flow characteristics, where we have turbulent flow. In all of these regions, we can still say that convection is still like conduction through those first layers of fluid, because even if we have turbulent flow, the fluid at the surface is still stopped. So kind of that argument still works. But what changes is we're going to have to basically try to capture the two different regimes in our modeling and be able to figure out, okay, in this part of the plate, we have laminar flow and it behaves this way. In this other part of the plate, we have turbulent flow and it behaves completely different. So we'll have to capture both of these flow regimes in our models because the behavior is going to be super different. And essentially what that means is we'll have to know where on our, if we're looking at an object, where on our object the transition occurs, so that we can say, okay, on this part of the object, it's behaving one way. On this other part of the object, it's behaving a totally different way. So we'll look at that. That will be next time. So for right now, we will, I'm going to pass out the quiz if you want to put notes and stuff away. You should have your notes from your notes for the quiz. So I'm going to pass this out now.
Yeah, and like RCC social, that like get close contact with you literally can't play for the games. So it's like
One person gets the wrong
yeah. So we're not allowed to go home.
Okay. So I just sent the quiz to you, Josh. So let me know if you get it. So just a couple of notes about the quiz. There's the potential that you might have to use some goofy function. There is also the potential that you might have to use like this weird BO equals goofy squiggle, tangent, goofy squiggle. Remember that one?
Yeah.
So there's the potential for both of those. If you look at the second page, there's a table that calculates those for you because I'm not expecting you to have a calculator that can do that. So there's a table of earth values and a table that calculates squiggle given, like, so if you know the BO number, it tells you what squiggle is.
Squiggle, can't squiggle.
We need variables called squiggle, because then it can do that, but
Isn't
you can with over the negative one.
I think, yeah, you're actually gonna hit -10
Instead of like 5. So you'd be better off not. Because then you just get 0.
All right.
I know that has 0.
You should probably just drop the class at this point.
It's kind of a.
Here, I'll just turn my quiz in.
Okay, so the other comment that I'll make, so the second page has values calculated for squiggle and for the error function. The other comment to make is I care much more about your process in selecting a model and finding the right model than, okay, maybe I messed up in the algebra of one of these big ugly equations. I'm less concerned about that, or you plugged everything in right. So make sure you give yourself enough time to, like, if you got all the equations right and didn't have time to plug it in or something like that, that's a minor thing. But focus on, make sure you're selecting the right model, analyzing which model, like when they work, when they don't, for this. So draw a picture, give yourself some time to really think about what's the best plan of attack for answering the question. If you do have any questions about how to use one of the tables or something like that, feel free to raise your hand and shout. Okay, so just to stop you, there are two numbers that maybe you have written down, maybe you don't. If you don't, they're up there, the Fourier number and alpha. If you do end up using one of the tables, there's no need to interpolate. Like, just pick the one that's closest. Okay, 15 minutes left, so still plenty of time. Thank you, sir.
was having difficulties with the Excel. And I was wondering if either you could look at it with me at some point today. If I could just turn it a little later.
Yeah, it's probably the easiest way. So often it's like,
I know what the problem was. I just don't know how to fix it. Okay. Well, there could be two problems.
often it's like something super small, like super small. So just email me the file because I've looked at a lot of these.
Okay.
So it only takes a couple minutes to figure out, oh, okay, it's this.
Yeah, basically some of my formulas weren't like right. They were off just by what cells they were referencing.
Thank you.
So then when I like, put in my estimates and did the iterative thing, I just have weird hot spots where it should be more, like of a gradient. And then like when I went and fixed them, it just didn't really fix it. And I tried to like put in another like estimate guess to have it try to read, and I still not getting it to look right.
Shoot me an email, just attach
Okay.
the file and I'll take a look at it. It usually only takes me a couple of minutes to figure it out because
Okay.
I know the most common problems.
Okay, great. Thank you.
So just send me that. And if I can find it right away, I'll just send it back like, hey, cell R5 should have been this or something like
Yeah,
that.
like-
Or if it's something bigger than that, then we can set up a meeting.
Yeah, what is like for your get like for just guessing? Like, are you just in terms of like the initial like, values before you do the calculation? Like, is there really a good method for?
It doesn't really matter.
Okay, if it doesn't matter, then yeah, hopefully you can fix mine really quick.
Yep. Thank you, sir.
Thank you.
Okay, like 5 more minutes. If you're still not totally wrapped up, if you're close, great. If you're a little further away, just remember, like, make sure your decision process for which model you pick is clearly communicated. So I know like why you picked what you did.
I don't have this staple. Do you have a stapler up here?
Do not
I
just,
tore mine apart too.
okay, that's fine.
Mine.
Oh, for the quiz, yeah, for your quiz, I don't.
Oh, the quiz.
Yeah.
For that one, I don't think we have one. Just set it here
Oh,
and I'll be very careful and not drop it. And if I do, then you're the only person that did it.
and I just get an A. Yeah.
That's good. All right, have a good holiday weekend, everybody.
That's all right if I just turn to my in-class assignments late. Right after class.
Yeah. Just upload them to Moodle is probably the easiest.
There was one, the one with the colors, the one I handed out.
Yeah, yeah.
I think I forgot to turn that one in
Okay.
a couple of weeks ago, but the other two were just the ones that were on today.
Okay.
So I'll just turn on through those. So. All right, thank you.
Okay, thanks. All right. In class here.
This is
That guy there, quiz there.
so I did redid the whole thing again.
Oh, you did?
Stayed it up and did it.
Okay.
So
Did you get it to solve?
yeah, I just not gonna click save because we'll see what happens with that. I just copy and pasted it to a Word doc.
Okay, that's perfect.
Can I also copy and paste my work for C to a Word doc?
Yeah, if you want, or however you did it, either copy and paste that into a Word doc or like write out what you did.
Okay.
If you want to do it by hand, this assignment doesn't have a whole lot of like by hand stuff.
Yeah, but I just want to make sure that it looks right before I start.
Yeah, it does. So when you save it, then it goes to crap.
Yeah, this is upload pending right now, so we'll see.
Exciting. But yeah, that looks right, Nolan.
All right, did you get a chance to check out my Excel sheet?
You mean that one? So what I'm
Is it that
doing,
one?
so it is. So once you get this, you can't ever come back.
Well, that's not what I wanted to hear.
So the way that you do, so I'm doing it right now. It doesn't take that long.
Okay.
But what you have to do, like this equation is still good. So
Yeah.
I'm copying that equation and pasting it into, I made a sheet that is the same shape, but just 100 everywhere.
Okay.
Some value. So that then it's not, because what happens is it's because of the like iterative calculation that it goes bad. So if you just like fix these to numbers, then they kind of all
And
play
then
nice.
just copy and paste them all.
And then I'm copying and pasting the edges, and then you can make sure that the edges are all like working right.
Yeah,
So
because those are the different ones, but once you get in here, you
the
can
middles
just
are all
kinda,
super easy.
Yeah. Okay.
So you get everything, and it'll be done in a second, but you get all the edges working right. Not that.
I just want to make sure what I sent you was right because I had a few files.
Okay. You just sent me one?
Yeah, it should look like that when you open it, but there's two sheets too. So.
I've got you though.
Anyway.
I can.
So it'll take me a little bit to figure it out, probably. I see like one. Ooh, yours is fun. So this looks most likely like a parenthesis issue, Jared.
Okay.
So the way that I fix this typically is it's usually not the inside. Like,
Right, that's the easy one.
so you can usually see it easier if you make the inside all just a constant.
Right.
So we'll make the insides all 100. Oh, screwed up. Outside. So I just am like,
Which that's what I did. I don't remember what value I chose, you know.
yeah, whatever, it doesn't matter. I'm just making the inside some fixed value so that, right, thanks, Emily. So that then you can take it and basically like, it should be close to that value everywhere. So the ones that are super far away, you probably have some mistake.
Okay.
So like, let's look at, this guy's 150. I
Mhm.
promise you that's not supposed to be,
Yeah,
right? Because it's supposed to
right.
be the average of the ones next to it.
Right.
Like this one, the 180s down there.
Yeah. Like some of them
It
were
should be an
changing-
average between like 100, or it should be between 125.
Right.
So then you just have to go and search and find, so they're 250 instead of 25.
Oh, there it is.
So you're having convection at 250. So that should have been a 25. So maybe that was on all of those. Okay, there's this guy, there's a 252. So
That
that's
could be the
usually
biggest,
my
yeah.
strategy. The other thing that I see, and I saw this on yours too, Jake, the BO number that you use to like weight convection
Mhm.
is, so you have it.
I was gonna be honest, we kind of worked on this together, which is why they look
Yeah.
So it's like
okay.
25, right?
So the BO number, I'll go to yours because you have it
Yeah, I have the
calculated
numbers on there.
separately.
Yeah, the two different ones.
So 1400 divided by 55.
Mhm.
So that's the BO number. That's H, but it should be HL over K,
Okay.
not just H over K. And your L is 1, but it's 1 centimeter.
Okay.
Oh,
Right. So then
okay.
it's like
So it's
14.
like 1400 times
0.01.
0.1 divided
Yeah.
by 55.
I said it,
This is 75
1 centimeter.
times 0.1. That's the size of each of your boxes.
Okay.
In meters,
The
I'm gonna be
centimeter.
0.01.
0.01.
Use, yeah, okay.
Yeah.
0.1.
Sorry.
I thought I did that. Okay, 0.01. So
Mhm.
that should some of it. It looks like you have some of the same. So these all look pretty good. This one looks like it might be wrong.
You gotta give some guy's calculator back when I
Anyway,
borrowed.
so yeah, so that's basically my strategy is you go through, you make the middles all 100, and that usually can help you because you know it should be between 100 then and
Be
whatever.
like an
the-
average.
Like that middle should be 250. So
Right.
those all around the edge should be between 100 and 250.
Right.
And all around the outside edge should be between 100 and 25.
Mhm.
And if there are any that look like super off, you go, oh, that's weird. And then you can go in and usually you
Check it
find like a
out.
parenthesis error or something like that.
Okay. Thank you.
Cool.
It's only, yours is still solving, so it should be fairly easy to fix.
Yeah.
Jake's went all to ref, so then it takes a little bit more.
Yeah.
But yeah, that's basically what I'm doing is going through and
Yeah.
finding that. Like sometimes, so this one should be a half times the top one. This looks like it's maybe wrong. It should be a half times the top, a half times the bottom, and then a full times that right one,
Mm.
which it is. And then it looks like you have an extra half right here. You have a half times G7 times a half.
Right.
Fixes it.
Nice.
So you're finding ones like they should all be like they are now, pretty similar.
Right.
These guys should all be pretty similar. So if you see ones like that one and some of those, it's probably when they're really different.
Should
It's
this not
probably
be
the
more
wrong equation.
drastic on the corners?
Not really, because it's set like this is fixed at 100.
Okay.
So this is going to be, this guy is an average between those two and 25.
Right.
So it's going to be a little bit lower. So
Okay.
they should all be like ballpark-ish the same. The corners are going to be colder.
Right.
In this part too, like they should all be ballpark the same.
Right.
The corners are going to be colder.
Yeah, no, I knew it was wrong.
Yeah, so
I mean,
but this is where like you can find which
Like,
specific cell is
yeah.
the mistake in.
like this before was hotter, you
Yeah.
know, than that. And that didn't
So
really make
for
sense.
example, for this one,
Is it
this looks
250?
right. Okay, so this one is, this corner's wrong because this is actually touching
Oh,
the
Right.
inside edge too. So you have to have plus the BO number
right.
times 250. So you have to, right, so the same that you did here.
Right.
So this equation, basically, you're going to take this equation and copy it into those four corners.
Okay. Yeah, so this one's right, so I can,
Mhm.
okay,
Yeah, so then you're copying those equations in and then just, okay, kind of rearranging some stuff.
cool. Cool.
So it looks like, yeah, I mean, this is the problem and this is why we don't actually do this in real life,
Mhm.
because you end up with like all these stupid things that,
Yeah,
but
it wasn't like that bad, but like I made just literal copying errors, which could be some of it. I feel like we fixed some of those, but
Yeah.
I guess I did. But like I had it, you know, some of them referencing inside here, you know, because I dragged some of this
yeah, you
stuff in
click and
there.
drag and copy it.
Yeah, and so I just
So I
made
don't,
problems for
um,
myself.
yeah, if you have issues, it looks like we found most of the errors.
Yeah.
If you have issues still, just let me know.
Okay.
These guys, yeah, I don't want you to spend like weeks figuring this out.
No, I mean it should
I
take
think
me a
it's
good,
just
honest hour.
those-
I think, Matt. You know, if I
Maybe
start
not.
from
Yeah.
well, if I start from here, then it'll take me 15, 20 minutes. But if I start from here, maybe going back over, we'll see.
Yeah.
A slow worker.
Yeah, But hopefully it doesn't take too long. If it is taking too long, just reach out. Because the goal is not a super long time futzing with Excel. The goal is to like, I mean, spend some time, okay, because you have to, but the goal is more to see like a little bit of a window into the process of how things that are actually designed to do this are actually doing it.
Cool, thank you.
All right, thanks, Jared.